Yeah, good morning. Good morning.
Good morning, sir.
Are you
Morning, sir.
getting PPT common bus system for four registers?
Yes, sir.
Yes, sir. Yes, sir.
Yeah, okay. So last class we have discussed this one. For your better understanding purpose, I'll repeat one more time. This is very very
Okay, sir.
easy. This is very very easy at the same time, very simple, and this is very very important also. If you see why we need to go for common bus system, actually we have a bus transfer mechanism is there. So bus transfer memory is transferring from one register to another register. This is one register, this is another register. If you transfer the data from one register to another register, if you take a 4-bit representation, so 0 1 2 3 4-bit representation, this is 4 bits in register A, 4 bits in register B. And then if you want to transfer this data to this register B, we need four wires, one, two, three, four wires. And the same data is transferred from register A to some register B. We have to take one more register, that is C. So this is 4-bit register 0 1 2 3. This is 4-bit registers. If you want to transfer the data from same data from register A to register C, so we have to link like this. Again we need four wires. Then if you want to transfer from C to B, again we need four wires. This is for 4-bit representation. This is okay, we can understand easily. So if you take 8-bit register, so if you take 8-bit register, for suppose for suppose so if you take 8-bit register, see, 8-bit register. So how to represent 8-bit register? We know that 8-bit register 0, 1, 2, 3, 4, 5, 6, 7 bits, right? So this is register A. This is register B. Register B with same bits 1, 0, 1, 2, 3, 4, 5, 6, 7. How to transfer from register A to register B? So this is connection, this is another connection, this is another connection, like this. How many wires we need? 8 wires we need.
8 bytes we need,
Okay,
sir.
this is 4-bit. We can represent the same representation can be done by using this 8 links. It is a it looks like some complex, right? So that so because of this complexity, we need to go for a common bus system, right? Common bus system. So the common bus system, the memory transferring from one bus to another bus, the common bus system using 4-bit registers can be represented like this. The common bus system for four registers by using multiplexers 1, 2, 3, 4. This is MUX multiplexer 0, multiplexer 1, multiplexer 2, multiplexer 3. Four multiplexers and four registers are there. A, B, C, D. Four registers are there, right? So draw this one first, next draw this one, right? So from the register A, we can represent this is 0-bit A naught, this is A1, this is A2, this is A3, and the same we have to represent similarly the B naught, B1, B2, and B3, right? So here we are representing C, C naught, C1, C2, and C3, right? And the last one is D register D naught, D1, D2, and D3. Like that, we have to represent all possibilities. This means that the output of this A register with 0 is A naught. The output of this one is A1. The output of this one is A2. Like this. The register from the A register output A naught. The output of this A naught is acting as a input of this register. Input of this multiplexer, right? So if you connect this one A naught, all these 0, 0, 0, 0 to A naught, A naught, right? A naught, like this. Multiplexer 0. A naught, connect this one, and see, see how to connect this one. See, like this. We will start from here, right? So this is if you take for suppose if you take all the representations 0 1 2 3 0 1 2 3 like that, if you consider this one, this is the D register. It has 4-bit representation 0 1 2 3. So I need to connect this all 3 bits like D3 C3 B3 A3 to register what multiplexer 3. So how to represent 3 3 3 3? What is the meaning of this one? The output of this D register D3 is acting as an input to the multiplexer. Okay. Next, the output of this one is acting as an input to this one. The output of this one is the output of A is acting as a. This is for one repr, right? This is for register. What is the multiplexer thing? At the same in the same way, if you want to represent this one, all twos are there: A2, B2, C2, D2. The D2 is connected to this one, C2 is connected to this one, and B2 is connected to this one, and A2 is connected to this one, right? Like A2 is connected to this one, right? In the same way, all ones A1, B1, C1, D1. So all ones all selected from these registers. These all ones D1, C1, B1, A1. All these are outputs of register is acting as a input to the multiplexer, right? So at the same way, A naught like that. We have to. This is for 0. This is for 1. This is for 2. This is for right. This is for what? So 3, right? So if you give 0 0 0 0 0 0, so 0 0, if you give 0 0, it is acting as a 0. So means it means we have to select A0, select A0, A1, A2, A3. If you give 0 0 0 0, this is this bit A0, this bit A1, this bit A2, this bit A3. Okay. So A naught, B naught, A naught, A1, A2, A3, right? All these are selected, so that it means that A register information is selected, and that information is sent to the bus line. If you take 0 0 0 1, 0 0 0 1, so 1 represents this one, right? So B0, B1, B2, B3. So the B register information is sent to this bus, and 0 0 1 0 C. C means C0, C1, C2, C3. The C information is stored here, and similarly, and 0 0 1 1, it is 3. So that what is it? D register. So all three is 3 3 3. All threes are connected to D register. The D information is stored here. Okay, right? So this is about how to represent a common bus system for the register. So this is the internal process. So actually, if you want to pass the data from register C register to R1, how to represent? First, the C register data is stored in the C or A or B or C data is stored into the bus. Then the bus output is sending to the register some R1. This is happening inside the common bus system for 4 register, right? So this is about 4 registers. Next one, we have already, this is for 0 0. We are selecting A 0 1, selection, so register B selected, 1 0 C selected, 1 1 D selected, right? So next, we have to use one more method for the common bus system: tri-state buffer. Tri-state buffer, right? So this is the tri-state buffer. We have three conditions are there: 0 is one output, 1 is another output, and one more thing is there: high impedance. High impedance is there.
Sir,
Hello.
so वो कौन सा चिपका कर బస్ కంట్రోల్ గురించి ఒకటి
Ah,
అది వచ్చిన డౌట్ ఒకసారి అడగచ్చా?
okay. You do one thing. You better to call me. Call to my mobile. I'll clarify. Okay.
యా ఓకే
Oh,
సార్.
okay, okay. Right. This is tri-star buffer or a three-star buffer state, right? So for suppose this is normal input, this is a control input. If it is how y equal to a, if c equal to one, if it is c equal to one, the output will be generated. If it is c equal to zero, irrespective of this input, it will not generate any output. You have to remember this one. Next one. So this is about high impedance. We know that. So this is the common bus system using decoder and a tri-state buffer, right? So here, this is the one of the representation. So we have how many tri-state and tri buffers are there? One,
ఫోర్.
two, three, four. So this is for A naught, this is for B naught, this is for C naught, this is for D naught.
డి నాట్.
So okay, this is for decoder. If you give n inputs, it can generate 2 power n outputs, but out of 2 power n outputs, the one bit is selected, and remaining bits are deactivated. For suppose if you give 1 0, if you give selection lines 1 0, so 1 0 means what? The two
1.
1 0. No, 0 0 1 0 means what?
సార్ 2
C.
సెకండ్స్ సార్.
Yeah,
2.
yeah. 2. This is selected. This is in active mode. Remaining set to deactive.
0.
So if you give 0 0 1 1, this is
3.
active. This is active. This
And remaining
is
not detective.
okay, deactive. Once you give this one, okay. So 1 1. This is the line. This is the input. The output of this one is decoder is acting as input to the tristar buffer, right? If you give one, whatever you have to give here one, that is generated to the bus line for bit 0, right? So if you give 0 0 1 1, this line is selected. So for suppose d naught is 1, the 1 is sent to this bus line. If we give 0 0 1 1 0, this one is selected. So this one means what? C naught selected. If you give 0, the C naught, the input is sent to this bus line. And so what about this one? 0 0 0 1, B not selected. For suppose one, the one is sent to the B naught line is selected, and that information is sent to this bus line. Like that we have to give. So the enable inputs are, if it is 1, then only this process is going on here. If it is 0, irrespective of this input, it will not generate anything, which means that high impedance, which means that high impedance. Next, one more important topic is that today's class, we have to discuss about arithmetic micro operations. This is very very important in general C language. In mathematics, so what are the different types of arithmetic operators? Is plus, minus, into,
Into division.
division, modulo. All these are different types of arithmetic
Yes,
operators
sir.
in general mathematics. Whereas in the case of arithmetic micro operations, towards the registers, which means that the arithmetic micro operations perform arithmetic operations on the numerics, what are the existing inside this register, right? For suppose one arithmetic operator is that add micro operation, add micro arithmetic operation. For suppose we have R1 is one register, R2 is another register. If you add these two, the sum of these two register can be stored in R3. And one more arithmetic micro operation is there, subtract micro operator. We can represent like this. Basically, subtraction means, for suppose we are using like this in mathematics, A equal to B minus C, or A equal to B plus C. Like this, we can represent in general mathematics. This is equivalent to this one, and this is equivalent to this one, right? But here, the subtract micro operation can be represented like this. So R1 minus R2, okay. The subtraction of these two, the resultant is stored in this R3, right? This is the one more but here in arithmetic micro operations we are using this R3 reverse arrow replacement operator R1 minus R2 can be represented like this, can be represented like this. So if you see here R2 dash, this is complement. We have a for suppose 0 is R2 value, we have a 0 is R2 value, R2 bar, R2 bar means complement of this one, which means that 1. So if you add after complement plus 1, this is 2's complement, this is 2's complement. If you perform,
Sir,
yeah.
so the R1 plus of minus R2 plus 1 ni
Yeah, yeah.
last sum.
This can be represented like this. Okay, right? So which means that R3 reverse R1 minus R2, this can be done like this. The complement, the two's complement of second, the two's complement of second operand can be added to the first operand, and then the result can be stored in this third register, right? That's right. This is the representation of subtract micro operation. Subtract micro like that we have seven micro operations are there that are. So this is one arithmetic micro operation. This is a symbolic designation, and this is the description of this one. So R3 reverse R1 plus R2, which means that the content of R1 plus the content of R2, these two are transferred to the R3. Already I told this one, the
R2.
content of R1 minus R2, these two once you do this one, next one transfer to the R3, right? So if you see here, already I told the complement of the register can be stored in R2. See the complement that contents of R2, one's complement, this is equivalent to one's complement, this stored into this R2, right? And two's complement, how to do two's complement, already one's complement is there. So if you add one, we can get two's complement. So the two's complement, that content of R2, which means that negate, right? See R2 bar plus 1, this is two's complement of the register R2 can be stored in R2, right? Next one. So if you see here now, this is the meaning of, can you tell me what is the meaning of this one? R3 replacement R1 plus R2 bar plus R1. Oh, this is equivalent to which operation? Hello, this is equivalent to
Whose
which operation?
complement plus R1?
Yeah,
Subtraction, sir.
yeah.
Subtraction, sir.
Subtraction. It is equivalent to R3 replacement R1 minus R2. But here we are
Yes,
representing
sir.
that subtraction can be represented like this.
R1 plus
Yeah,
complement
yeah,
R2
yeah.
plus R1.
Yeah. That the two's complement of second register can be added to the first register, and this summation is sent to this R3 register. Okay, R1 plus
R3.
R1 plus the two's complement,
Whose
right?
complement of
R1
R2?
R1 plus two's complement of R2, which is the meaning of subtraction, right? R1 reverse arrow R1 plus
Sir,
R2.
welcome plus 1 plus
So, okay, R1 reverse arrow R1 plus R2, this is increment operator. It's like a for suppose if you see in the C language, what is increment operator? A plus plus we can represent A plus plus. How to do this one? A equal to A plus 1, this is the meaning of A plus plus represent A equal to A plus 1. In the same way, R1 reverse R1 plus R2, this is the increment, increment the content of R1 by 1. Okay, here increment the content of A by 1, right? So next one, R1 reverse R1 minus R2 decrement the content of for suppose A minus minus. How to represent this one? A equal to A minus 1. We are decrementing 1 from the actual amount of actual value of capital A. This is about R1 reverse R1 minus R1 minus 1. This is about all these are how many? 1, 2, 3, 4, 5, 6, 7. 7 arithmetic operations happening inside the registers. Okay, this is about my arithmetic micro operations. Okay, so next, so these operations are
Sir,
how these operation. Yeah, yeah. How these operations are executed inside the
sir,
register. Yeah, yeah. Tell me.
sir, అక్కడ R1 plus
R1,
sir, R1 plus R2 bar plus 1 ఉంది కదా సార్ అక్కడ
R1 plus
R1
R2.
పైన సార్ పైన
Yeah, yeah.
R1 ప్లస్ అదే సార్
This
అక్కడ
one.
ప్లస్ 1 ఉంది కదా అక్కడ ఇంప్లిమెంటేషన్
No, yeah. If you give for suppose how to for suppose R2 equal to 0, I need to do that. What is that? One's complement like this. So how to do 0? One's complement. What is one's complement? 0 is replaced with 1. Ones are
R1
replaced
plus
with
R2 bar plus 1
0.
సార్
Yeah, I am telling you that R1 plus this one. This is R2. Okay, which means the R2 complement plus 1. This means 1's complement. If you add, for suppose this is 0, R2 equal to 0, 1's complement 1. If you add one more 1, if you add one more 1, that is 2's complement, na? Did you understand? Hello? Hello?
Yes, sir.
Yes, sir.
Who is asking doubt? Who is responding? Did you understand? Who is Prasanna? Who is, hello? Lal?
Sir.
Who is asking doubt? That man left from our meeting or what? Okay, anyhow.
No, sir. He is
So
there, sir.
yeah, yeah. You remember while teaching to in the class, don't disturb them. If you speak meanwhile, we may be get some disturbance and uh, we may get some disturbance. That's all. Okay, this is about very
Okay,
clear.
sir.
ఓకే సార్
Very clear,
ఓకే
very
సార్
clear. R1 plus R2 bar plus 1 means, for suppose if you take R2 equal to 0, R2 bar means 1's complement. What is the meaning of 1's complement? Zeros are replaced with 1's. 1's are replaced with zeros. So that R2, we are getting to 1's complement. So that 0 is replaced with 1. Again, we have to add R2 plus 1. R2 result is there. This is 1. 1 plus 1. If we add one more 1 to the 1's complement, that is 2's complement. That is 2's complement. So that R1 plus 2's complement of R2. 2's complement of R2, which means that subtraction. Right?
ఓకే సార్
So, okay. So, this is about
ఎస్
micro
సార్
operations. Please, please, someone is. Um, okay. Next. Now, how these operations are executed inside the adders. Now we have to take so if you want to perform any operation, binary operation, we have to take two operands. For suppose plus is a binary operator or a unary operator, can you answer this question? What is plus?
బైనరీ ఆపరేటర్ సార్
Binary operator. Why it is binary operator? Why it is binary operator? Without two operands, we cannot perform this one. Yes or no? A plus
Yes, sir.
ఎస్ సార్
A plus B. This is one operand.
ఎస్
This
సార్
is another operand. So binary, we are taking two operands. In between, we are using one operand, that is plus. So this is binary operation. Right? For suppose R1 plus R2 in stored in R3, we are performing binary operation here. Binary operation, so that the resultant can be stored in this part. Right? So here we are taking binary adder. We know that about binary adder, it is a digital circuit that generates the arithmetic sum of two binary numbers of any length is called binary adder. You'll see in the diagram, very easy. So here this is R1, this is R2. So consider 1101. This is the input of this one R1. This is the another input of R2. This is user defined. You can take any binary numbers. I am taking this one 1101 0110. Right? Now, initially, this is the C control signal. The carry is set to 0. the carry is set to 0. See, set 0, 1 1. The binary adder, how it, what it gives, the binary adder gives 1 1. If it is 1 1, 0, the output sum is 0, the carry is 1. The carry is 1. 1 plus 0, 1. 1 1. If it is 1 1, see, the carry is 1 plus 0, output is 1. 1 plus 1. Don't tell what is that. 1 plus 1. 1 plus 1, 2 kada. So 2 means so 1 0. So we are taking this one 0 0. This one is carry, right? Oh, again 3 ones are there. 1 plus 1, 0 0 0 1. Okay, again we are getting carry, so 1 plus 1, right? 3 ones are there. If it is 3 ones, we can get 1. Again one more 1, carry 1. Next, so 1 plus 1, 0. So 1 carry is there. So 0 plus 0 0. So 0 1. Remember, c equal to 0, 1 1. If 1 1 is there, 0, then carry is 1. Next, again sum of these three. Okay, so don't assume 1 plus 1 equal to 2, 1 plus 1 plus 1 plus 1 equal to 3. Don't assume like that. See, 1 1 0. If it is 1 1, carry 1. Next 1 1, next 0, carry 1. 3 ones are there. 3 ones are there. So that 1 and 1, and next one the carry is 1. Next 1 1 0, carry 1, right? So this is about binary adder representation. Binary adder represents how this this calculation is happening inside the binary adder. We can see by using this one, 4-bit binary adder. 4-bit binary adder, how many bits we are taking? 1 2 3 4. 4 bits we are taking. So that 4 bits, 4 full adders are there. 4 full adders are there, right? 4-bit binary adder. See here, this is the full adders, 1 2 3 4. Full adder taking 3 inputs. One is carry, and one is a naught and b naught. After taking these three, it calculate sum. After sum, it gives a carry. It gives a carry. If you see here, c equal to 0, a naught equal to 1, b naught equal to 1. Yes or no? C equal to 0, a naught equal to 1, b naught equal
We
to
are
0.
equal to 1.
B not equal to, what is the sum? 0. S not 0. What is the carry? 1. See, this carry. Okay, what is 4-bit binary operator? What is 4-bit binary adder? So the definition of the 4-bit binary adder is, so which means that the collection of full adders, all these are different types of full adders, all these are collected, right? The collection of full adders which are connected, in a cascading manner, means one by one, where the output of one binary adder is acting as a input to the second adder. For suppose this the second adder output carry is acting as input to the next one. The third one, the output of this carry is acting as input to the next one, right? So here the full adder will be added to the next full adder like this. The full adder means it supplies 3 bits. One is 1 2 3, 3 bits. We can get one sum and one carry, right? If final carry is 1, if the final carry is 1, right? If it is negative number, if it is negative number, right? So then we have to represent that number in a 2's complement. We know that we know that r1 minus r2, we know that how to represent that one complement of this one, complement of the 2's complement, the 1's complement of complement, the number is called as 2's complement. We can represent that negative number, right? If it is carry 1, we can represent a negative number, right? If it is 0, the carry is 0, that is positive number. no need to change the number, no need to change that number. See, so if you take for suppose 0 0 1 1 0 and 0 0 0 1, let us consider this one. So what is this? This is a naught, this is a1, this is a2, this is a3. What about this one? B naught, b1, b2, b3. So then apply 4-bit adder representation. 0 1, 0 1 means 1. What is carry? 0. So next 0 1 plus 0 plus, here we can understand easily. So here 0 1, 0 1 represents 1. Okay, carry 0 is there. Again we have to do carry. If you take 1 1, so 0, otherwise you can take 1 1 0 1 1. Take this one. 0 0 is here. 1 1, if you know that if it is 1 1, 0 carry is 1. Next 1 1 0 carry 1 1 1 0. So this is 4. So 1 1 0 1, 1 carry is there. So this is the negative number. It indicates that negative number. If it is negative, we have to represent that number in 2's complement form. If it is negative, if we get 1, that is negative number. This number can be represented in 2's complement form. Okay, same thing happening here. A naught 0, B naught 1. What is the carry? 0. What is the sum? What is the sum? 0 1 1. 1 is there. What is the carry? So 1. After that we are giving carry to 0. This 0 to here. This example is for this one. I am taking this one. So if it is 0 here, again 0 1 1. So a value is 1, b value is 1. So if you take 1, so sum is 0, carry is 1. Like that we have to perform. After end of this, the next last one getting 1. If it is 1, negative number. This is about 4-bit binary adder. So how to represent, how to what you get this one by seeing this example, right? By seeing this example, what you get? A, we are getting a plus b plus the carry 0. This is about, we are giving a plus b plus c, sum s equal to. This is 4-bit binary adder. 4-bit binary adder. Remember, adder, right? This is about, we are using all plus operators here. Next, how to represent 4-bit subtractor, adder subtractor. How to represent binary adder subtractor? We have to take this example. So subtractor, you know that adder r1 plus r2. The next subtractor micro operation can be done here. R3 tends to reverse arrow r1 minus r2. This is minus r2. This can be represented in 1's complement of r2 plus 1. If you add plus 1, this is the 2's complement. The 2's complement of second operand can be added with first operand. The resultant can be stored in r3. The resultant can be stored in r3, right? So this is about subtractor. So how we can represent that subtractor, 4-bit binary subtractor, adder and subtractor? This is the representation. We have to take 4 full adders. 1 2 3 4 full adders are there. Here we are taking 2 inputs, a naught, b naught. One more input is carry. 3 inputs are, right? So compared to 4-bit binary adder, extra we are taking here is that this is the. Can you tell me what is this diagram? We know, maybe compare to me.
XOR.
What is this?
XOR, sir.
XOR. What
XOR
is
gate.
XOR gate? XOR gate, right? This is the XOR gate. Here instead of B naught, previously we are using B naught, B naught. So in B position we are taking XOR gate, XOR gate, right? So here, so this is one input, The full adder can be take the input from XOR gate and A01 input and carry m value is sent to the C naught. The carry is sent to here. How many inputs are there? One, two, three. It is taking two inputs. It will give one sum and carry. Okay. Then what is the purpose of this XOR gate? Why we need to use what is the XOR gate representation? XOR gate representation. So here, if you observe here, this is the M. This is the M. So this is the input. M means what is this? M means mode bit. Mode bit, right? For suppose if m equal to 1,
Comparison 0 2 for subtraction, sir.
m equal to 1,
Comparison 0 for subtraction.
1 5, already what I told. So while teaching,
1 for
okay, we'll discuss later. M equal to 1, the circuit is a subtractor. If it is, you remember m equal to 1, if it is m equal to 1, the circuit is acting as a subtractor acting as a subtractor. Okay, so if it is 0, adder. If it is 0, it can be represented as a adder. So here, see here, for adder, for adder, for suppose for adder, so m equal to 0, take m equal to 0. So here m equal to 0, m equal to 0. How many inputs? So so I am discussing about this one. We have to calculate this XOR gate. So already we know that this is single output. We have to get this. We have to find this one. So m value is coming to here XOR gate. M value is input to the XOR gate. Yes or no? One more value is B naught value. So for suppose M XOR gate B. So which means that B naught, B1, B2, B3. M value is already we know that 0. XOR gate. If you take B is a 0 value, we can get a 0. Or suppose if you take 0, M value is already we decided 0. If the B value is 1, we can get 1. What is 0, 1? These two are values of B only. These two are, so so even though we are getting the input from M, so this entire XOR gate belongs to B. So that this output of this one value is belongs to B only. So if you use 0, 0, if you use B value is 0, we can get 0. If you use B value is 1, we can get 1. We can get 1. When the mode bit is 0, the mode bit equal to 0, right? So for suppose, how to write this one? Mode bit 0. So m equal to 0 colon a plus b. How to write this one? So how to write? So if a mode bit is 0, then the full adder receives a register b information. If it is 0, mode bit is 0, then add these two and receives a b bit information, right? So how to represent this one? So adder a plus b, right? A plus b, so plus this one carry. For suppose subtractor, for subtractor, so see here subtractor m equal to 1. If it is m equal to 1, we can understand easily. M equal to 1. So again we have to perform m XOR gate b. The problem is here. The problem is here. M XOR gate b. If the m value is 1 already, by default we decided mode value is 1. XOR gate, for suppose if you take 0, if you take 0, we can get a 1. 1 XOR gate 0, we can get a 1. If you take 1 plus, if you take 1, we can get a 0. So if you observe here 1, 0, these two values, even though these two are inputs, 0, 1 and 0, we can get finally output of b only. So this is b values 0 1. This is if you give 0 we can get 1, if you give 1 we can get 0. If you observe this one, this is b dash values, complement of b, complement of b, right? So here, so this is about how to represent this one. So how to get this one? If m equal to 1, already we are giving a only, a. If m equal to 1, we m equal to 1, a plus what is the output of this one? If m equal to 1, what is the output of this one? 1 0. But actually what are the b values? 0 1. By seeing this this output 1 0, this is b bar, b bar complement, the complement b bar plus plus the carry, whatever the m value is there, that is carry. Already m value we are taking 1, so this m1 is sent to the carry plus 1, plus 1, right? M equal to 1, then the subtractor can be represented like the a plus b, a plus b bar plus 1. See, remember, don't confuse. M equal to 1, we are taking m equal to 1, that 1 is sent to here. Okay, the m equal to 1 input is acting, the one is input is acting to the input is acting to the input of XOR gate. 1 is here. Okay, 1 is m value, b value is suppose 1 here. So 1, if you take 1, b value is 1, m value is 1. So if you take 1 1, so we can get a 0 in XOR gate. That is one representation. Next, if you take same 1, if you take b value is 0, b value is 0, we can get 1 XOR gate 0 1. Okay, the output of this one is 1. If you see, if you b value 0 1 అయితే, so b bar value 1 0 వచ్చింది. What is the what is, by seeing this, what you can understand, this is the complement of b, so that this is the b naught complement. Okay, so complement b naught. Next a naught is there, next c naught, whatever m value is there, that is sent to the c naught, so that a plus b dash plus 1, this is the subtractor. Addition, m equal to 0, m equal to 0 means, if it is m equal to 0, so m equal to 0 means we are not so m equal to 0, see, m equal to 0 already I told. M equal to 0, what is happening? M equal to 0, m plus b, m value is 0 XR. If it is 0 0, next 0, m value default 0, you should not change, plus if it is 1, we can get a 1. If you see here, what are the b values? 0 1. After getting, after applying a XOR gate, what are the b values? 0 1 only. So there is no complement, so that we have to represent this one is just b only, so that a is one input plus b, plus b, when it is plus b, if m equal to 0, if m equal to 0, if m equal to 1, a plus complement b plus 1, right? So that this one is a plus b plus the carry, even if you want carry, we can add complement. Anyhow, this is 0, so that a plus b. Okay, this is about 4-bit binary adder subtractor, 4-bit binary adder subtractor, right? So here, see here, so this is also increment operator, we can see later, binary increment. So at a time, if you learn all these things, there may be chance to forget entire topics of all this binary subtractor and multiple, right? So increment operator, see, this is r1. Increment means r1 plus 1, we are incrementing. So add 1, 1 1 0, 1 carry, next 1 plus 0 1 0, next 0 plus 1 1 0, 0 plus 1 1. So here there is no carry, right? This is about increment micro operations, increment. Similarly, so how to use that binary bit binary 4-bit binary incrementer is there. This is the representation. We can explain next class binary increment. Next, arithmetic circuit, how it is going on internally. Next, like this. Okay, what is today's class? Did you understand today's class? We have different types of micro operations are there while um, performing on the data. Around we have seven micro operations are there. Okay, these are the seven micro operations. So the subtractor, how to perform, that complement of two's complement of second operator can be added to the first operator and then stored into the R3. So compared to all these three, this is somewhat different, so that I am teaching again and again, right? So next, this is the binary adder process. So if you take R1 and R2, so complement 110, like this, we know that maybe these are the basic operations, right? So next, right, next, 4-bit binary adder, we know that this one, the full binary, we are taking full adders. Four full adders are there. So every full adder taking three inputs. One is carry and two are actual binary inputs. So and generates one sum and a carry that is acting to that carry. The first carry of first full adder is acting to the input to the second adder, like that, and so on. Similarly, we can continue one by one in a cascading fashion. Again, the last fully adder can generates one output sum and generates one. If it is one, okay, it means that the carry is one. It is the negative number. The binary number can represent it in negative. If it is zero, it is positive. We cannot change the number, right? Next, binary subtractor. So this is the subtractor. We know that, I don't want to tell once again. So next, this is the subtractor. So again, if you want to teach, if you want to understand the subtractor, we have to use XOR gate operator. This is the XOR gate operator, right? So XOR gate operator, this is one input to the fully adder, this is another input to the fully adder, this is another input. Three inputs we are taking. So if m equal to 0, we know that m equal to 0, there is no changes in b. So b value is 0 with 0 0 0 with 1 1. Okay, if it is 0, if it is 0 um, if it is 0, we are not getting, we are getting 0 m plus. If it is 0, m equal to 0 0 0, m equal to 0 1 1 1. It is b value is 0 1, output also 0 1. So that so there is no changes in the b value, so that um, a plus a plus b. Whereas in the case of m equal to 1, the mode bit is 1. It is acting as a subtractor. So if it is 1, right? So if it is 1, the b value is 0, b value is 0, the output is 1. So if you compare with the output is b value 1 with in initial input 0, if you take 0, the output is getting 1. If you take 1, the output is 0, which means that the complement of b naught, the complement of b naught. If you take generalized term, the complement of b bar, right? The complement of b, which means that b bar. So this input is given to this fully adder. This is uh, input, this is one more input, so that we have to write how to write. So a, how to write this one, how to write, already we said next slide. So how to write this one, a m equal to 1, how to write a plus, this is anyhow, if it is 1, we are getting complement, 2's complement b bar plus 1. This is the representation of the subtractor. Okay, so this is about today's class. We have discussed what is 4-bit adder, or what is a 4-bit binary adder and subtractor. We have different types of arithmetic operations, and we have around 7 operations are there. So subtractor, increment and decrement, and complement, one's complement, two's complement. All these are different types of operations are there, right? Micro operations are there. Okay, this is about today's class. So I'll stop the class. I'll continue next with the topic, what are the different types of in next classes, what is the increment and decrement, how it is performed by using some circuits. Okay, so Lal, I'll stop the class. I hope you can understand this class. Okay, thank you all.
Thank you,
Thank
sir.
you, sir.
Okay,
Thank
okay,
you.
Thank you, sir.
okay, okay,
Thank you,
thank you,
sir.
Amma. Thank you. Did you understand this class?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, go. Okay. If you have any doubt, don't stop the class. Meanwhile, you should not ask any question. There may be chance to confuse all these remaining. So those who are understanding, they can get some problem. So okay. If you have any problem, better to contact to mobile. I'll clarify your doubt. Okay. Don't stop the class. Meanwhile, while I'm teaching interestingly. If you ask any doubt, your voice is somewhat what is that? Some murmurings are coming from your side, some disturbance is coming from your side. I am unable to understand your language, so that don't disturb the class while teaching. After this class, so you make a call to me, I'll clear. Okay, thank you all.
Okay.
Thank you.
Thank you, sir.